Hello everyone, it's June 17th. I'm back home. Alright, let's get this one done. What is this? Make array strictly increasing. Given two integer arrays, 1 and 2, return the minimum number of operations, possibly 0, needed to make array 1 strictly increasing. In one operation, you can choose two indices from I and j and do the assignment. Array 1 equals assign a value from array 2 to array 1 if there's no way to make it strictly increasing to -1. Okay, let's take a look. 1, 5, 3, 6, 7. Replace 5 with 2. Oh, okay. Yeah. What do you think? We need to make this one strictly increasing. So, I don't know. Maybe we need to figure out. Hold on. So in this case, 1, 5, 3, 6, 7. I mean, array 2 doesn't matter. So maybe we can sort array 2. Okay. If we sort array 2, and we can say 1, 5, 3. So 5 is bad. So we need to try to find a value that's in between 1 and 3. And we find there's nothing. Okay. Then what? So we replace 3 with 5 with 3 and 3 with 4. Interesting. What we want is the minimum number of ways to make it, right? The minimum number of operations. I mean, the most operations is just the size of array 2. Well, the minimum of size array 2 and a size array 1. I'm actually thinking about binary search. Like we say we'll have certain number of operations and just to see if we can make it happen. How do you think that can work? Because otherwise, you know what? No. Let me draw this. We have 1, 5, 3, 6, 7, right? Let's say if I want to know the total, the minimum number of ways to make this, right? If I know the total number of ways to make this good, right? The minimum number of ways to make this good. And then it depends on what this value is, right? If this value is smaller, then we need to swap it one more time. So that will be similar. Yes, I think that will work, right? So we just need to know the minimum number of this. So, okay, let's say we can do the minimum number of this is always 0, because by itself is always 0. Minimum number of this, we say this is 0, and then we choose, so this is also 0. So this is going to be 0, right? And this, okay? Then if I sort array 2, so array 2 is going to be 1, 3, 4, right? So we try to find, okay, we want to find something smaller than 3. So we can do 1, right? So the minimum of this is going to be 1. And this, it doesn't work, right? So what? We backtrack, we go back here, and if we go back here, we have nothing else to try. So we backtrack, we will go back here. Go back here. So we need to find someone larger than 3. Right? Find someone larger than 3. So okay, we say, but smaller than 6. So we say, okay, how about we try 4? Then we go down here. Then we find something smaller than 4. So okay, we can try 3. And then this we got 2. Huh. I am not sure. I mean, if you want to do it this way, we probably shall do it from low to high. Right? Like this is good as 0. And then we need to try to find this. And then for this, I need to find something that's smallest that's larger than this. So we find 3. Okay, so we say, so we can either swap it or not swap it, right? If I swap it, then it becomes 3. Then this will become 4. Then this cannot swap. Or if I don't swap, then we go here. Then we just did. That's a different idea, right? That means every single one you try to swap. So every value, you either swap or you don't swap. And when you swap, you binary search to find the smallest value to swap. I don't know, what do you think the runtime on this? And look at this. We have 2. So now in this example, we have to use a counter. Right? 1, 1, 3 has 2. 6 has 1. So 1 doesn't change by itself, right? So now we go to 5. So we can either don't change or we make a change. If we make a change, we can only change to 3. Right? So if I don't change, come next, we have to go for 6. And then boom, we'll be dead. If I change, coming here, that's a 3, so we have to find a 6. Come here, then boom, you're done. But each one you can change or not change. That's I don't know. This is a thought, right? This is a thought. Hold on. Can we do binary search? Let's say the maximum operation for this is 3. Okay. Then let's say we can start from 0 operation to 4 operation. So the first is 2. Right? Can we say we change 2 to make it possible? Is it possible to change 2? Yeah, that doesn't sound right. Yeah, it's more like backtracking, right? It's more like backtracking. I mean, we can try. Just give it a shot. Maybe it'll work. What do you think? So we definitely sort this one. That's actually not right. We need a counter. Okay, then we can say counter C2, right? Equals counter array 2. And then what? Then we will say def helper index. Basically, this is from this to the end. What's the smallest, right? So this is what we're gonna return. And then we say if index is larger, we can say n is len array 1. So if this is larger equal to n, then we don't return anything. Okay. Now whatever I am, then I need to find the smallest of the remaining, right? Okay. So smallest of the remaining. Now there are two situations. Either I do not change. So this is the first scenario, is I do not change. In fact, I don't think it shall return a value. I think you should say changes, steps, right? Operation OPs. Okay. Then we can say self.res equals the minimum self.res OPs. That's it. And then we can return this thing. Otherwise, okay, so I'm at index and I have OP. So I can just call helper index plus 1 OPs. I don't change. I don't change anything, right? Or I change. Now, how do I change? I need to change something that is the smallest possible, right? When I change, I want to change the thing that's smallest possible. And how do I change to a smallest possible? Well, I can say what is the smallest possible thing I can change into at the current rate. And now we say if index is equal to 0, right? We want to start. then the smallest possible is going to be the smallest possible is going to be the smallest of array 2, right? Then we can say if index is 0 and array 2 0 is smaller than array 1 0, then we're gonna make the change. How do we change? We say array 1 0 equals to array 2 0. Then we do helper index plus 1, OPs plus 1. We make a change, right? And then backtrack. I mean, we probably should just do index. No, this is 0. Put this as index. If index is larger than 0, then we need binary search. Doesn't matter. Okay. How do we search? Well, search on this counter. Oh, let's put it back here. So yes, this is backtrack by, oof, you change it. So original equals array 1 index. And I change, I do this, backtrack array 1 index equal to original, let's backtrack. Otherwise, if this is larger than 0, then we have the current restraint. Not really the current restraint. It's just basically we want to find the smallest possible. Okay. Okay. So if we find the smallest possible, and then we swap it, right? Then we go to the next one. Now we have to check something before we make decision. So the way we check is at the current position, I need to find, hold on. So there's a thing. If, right, index is equal to 0, or array 1 index is larger than array 1 index minus 1. If that is possible, then we can just skip it, right? We can skip it. Not otherwise, right? Or we try this. We try to find something that we can do. If we still have 0 and then this is smaller, then we do it. Or index is larger than 0. Okay, index larger than 0. Okay, we have some value, index larger than 0. Doesn't matter. If it's larger than, we already tried it, but now we gonna want to find the smallest possible on the array 2. So I'm gonna say j, okay, equal to bisect array 2 uniques. Okay, uniques shall be list C2. And then j equal to bisect right array 2. Actually, we need to do sorted. This and value must be array 1 index minus 1. Right? Then whatever it lands on, so we want to find something larger than array 1 index minus 1. right? Something larger than that. So whatever we land on is something larger than this value. Then we say if array 2 uniques j, okay, is uniques j is smaller than array 1 index. If it's smaller than that, then there is a reason that we do the swap. Otherwise, there's no reason to swap. If the value in array 2 is actually larger than the value in array 1, then you swap it, you won't get any benefit. So if it's smaller, then we can try swap. We can say original equals array 1 index. Okay, now we say array 1 index is equal to array 2 uniques j. Well, j has to be smaller. J is smaller to land array 2 uniques. And, right, so we swap. And we also have to counter to array 2 uniques j minus equal 1. And if not C2, then we delete. All right, we do all this. Then we say helper index plus 1, OPs plus 1. We did one operation. And after that, we're going to backtrack. How do we backtrack? Well, first things first, we are going to restore the value to original. And we have to do C2 array 2 uniques j plus equal 1. We add it back, right? We add it back. If it doesn't, right? If this does not satisfy, then we don't do it. Yeah. With this, we can just call helper. We start from 0, operation, no operation beginning, and then we'll return self.res. Okay, let's see if this makes sense. 1 5 3 6 7 1 3 2 4 should be 1. This is the same. 4 3 1 2 1 6 3 3 minus 1. Yeah. If self.res smaller than math, else minus 1. Okay, this one is array 1, array 2. Okay, we have some issues on this one. Okay, why I did not handle this correctly? Let's see. Index and OPs. Index is 0, index 1, and index 2. Index 2. No, index 2 is in 0, 1 because I hit this one first, right? And I hit this one on 2, 2, 0, and 2, 0, this one doesn't work. So I do this. No, it's not equal to 0. Then I do this, right? Then I do unique, 1, 3, 4. I'm at that 2 position, so I need to find something larger than 5. Then there's nothing. So that's 2, 0 comes in, and then I did 2, 1. Where did 2, 1 comes from? Is the first, right? This 2, I changed this. You know what? OP is not really necessary. I need to know array 1. Probably C2 as well. Okay. So I'm at this position, which is correct, right? And then I did not continue to do this. That's 3. Wait, why did I not continue doing it? I don't know. I am here, right? Counters, right? And a unique will be 1, 4. And array index minus 1 is 0 will be 3. 1, 4, 3. This one shall be true. And array 2, this is smaller. Ah, that's why. Index. Because these two are equal. I see. So how shall we handle this? Yes, this is an interesting case. So of course, if array 2 is smaller than this, yes. But if array 2 definitely can be larger than if array 1 index is equal to the previous one, right? God, how do I... If this and array 1 index is equal to array 1 index minus 1, right? If these two are equal, then whatever I find will work. Or they are not equal. Nah, it's not really equal, it's larger equal to, right? If array 1 index is larger, smaller equal to, if that is smaller equal to the previous one, then we have to swap. But if this is larger than this, right, this is OR, so array 1 index is actually larger than array 1 index minus 1, in that case, then we require the replaced value to be smaller. Otherwise, there's no point in replacing. So when you do that, then it makes sense. So now it is the question whether this is fast enough to handle everything. Well, I just submit. It's okay. We did it before, 2019, a long time ago. Based on the speed, I think it's now working. Okay, so we have to think about this again. Oh no, it's just wrong. It's just wrong. That is interesting. Did I not? Answer is 8. Dude, answer is 8. Huh. I don't even know what to do here. Index, OPs, maybe array 1. Index, OPs. I don't have enough. I already got 18 here. All right, hold a second. What's C2? C2, man. Okay. Hold on, let's see this. Let's draw it out. We have 5, 16, 19, 2, 1, 12, 7, 14, 5, and 16. And what we have is, what do we have? 6, 2, 17, 2, 4, 2, 3, 2, 16, 2, 13, 1, 18, 1, 7, 14, 1, 7, 14, 1. Okay. I never even swapped the first one. That's interesting. I haven't even swapped the first one and I already called it ends. Huh. Oh, wait, hold on. Array 2, 0, this is not right. You have not sorted this yet. This should be min C2. That is still not right. No. This should be min C2. Oh, let's just calculate it once. Minimum. Yeah, now it's right. It's minimum C2. All right, we should do this. Put this one here. Then we can say array 2 uniques 0, right? Array 2 uniques 0, and then we have to do exactly the same thing. Interesting. Maybe. Hold a second. How can we combine these together? Because we're doing exactly the same thing, right? I mean, in this case, we can say j is equal to 0, right? And then we do this. And we do this. Right? We do this. And the backtracking is exactly the same code. So the ideal is to try to make, like, I don't want to repeat this part, because these two parts are exactly the same. Can we, I don't know. I mean, we just need to find a j, right? So we have this. And then what? If this, then we say j equal to 0. Okay? And then if this, j equal to this. Okay, I have an idea. So we can do this only once. That's the whole point. So if this j equal to 0, that's fine. And of this j equal to this, if j is, we can say initially j equals -1. If this set j equal to 0, right? And then we can say this is going to be temp. Yes, it's the temp. Temp is smaller, and then it's going to be temp. Then j equal to temp. Right? Then we say if j is large equal to 0, then we do the thing. Okay, so this one is do not swap. Right? And this is find the best option in array 2 to swap. All right, try it again. Very slow. Time limit. Okay, so this one TLE. What do you think? This is definitely not making it look easy. But you need to not swap it. Maybe we only do not swap when the swapping will not result in anything good. How about this? Oh. How about, let's try this again. How about something like this? The same, if this is the same, yeah, we reconsider the not swapping part. So we do this, and then we say if this, yes, we swap, right? And then we do this, if this, then we swap. If j larger than 0, then we swap. Then we say elif index equal to 0 or array 1 index larger than array 1 index -1, then helper index +1 op. So this is do not swap. Nope. Why? It is the first one. That's weird. Because I mean, the first position. No, I don't feel this doesn't feel right. Because I can already think of a counter example to this. No. This is not right. What other idea do you have? I don't know. One, 5, 3, 6, 7. 1, 2, 3, 4. So if I don't know, 1, and then we can do 1, 2, 3, 4, 5. Oh, hold a second. 3, 6, 7. And in this case, any one of these, no, not any one of these, there's only this one, can make it work. I'm thinking about maybe monotonic for 1. Okay. Now we do 3, and then we do 5. Then we do 3, then oops. So I need to pop 5. Right? Then we pop 5. Then we need to find something that fits. But how about this situation? We need to pop 5. Right, and we have 1, 3, 4. We have nothing. Then we go back to 1. No idea. What's the hint? dp. All right, what's the state? Index in array 1 and the index of the previous element in array 2 after sorting and removing duplicates. So it's dp, but we need to do a smarter dp. Basically, this is what it's telling me. Whatever dp I've been doing is backtracking. That's why it's not working. Okay, so let's do it again. 1, 5, 3, 6, 7. And I have 1, 3, 4. So if the answer is going to be dp0, 0, okay, right? We want dp0, 0. So with this much to choose from, and given this much to change, what is the final answer? Okay, so now let's say what's dp01 given this to the end and this to the end. Choose. You cannot choose this. You can only choose this or this. I mean, 0, 0, it's easy to say, right? In this case, I just don't do any choice. Then I move on. And I move on, so the next has to be this and this, right? So the next one has to be dp11. So at dp11, we can say, okay, I'll what do you mean? What I mean is the j is pointing to the smallest value, currently unused smallest value. Okay, currently unused smallest value in j, and I is the current position. Then in that case, we can say, then when do I swap? When do I not swap? If this is better than this, I can swap. Or I can choose not to swap. And this is different from what it's saying. It's saying is the index of the previous element in array 2. Previous element in array 2. And the index of the previous element in array 2 after sorting it and removing duplicates. What do you mean about the previous element in array 2? Well, for one thing, right, it is every time you swap, you go from small to large. So the 2 pointer kind of go in that way. But what I don't understand is if I want to find out the minimum number of swaps, right? I mean, for one thing, if this value is larger than this value, then there's no swap. We just keep moving on, right? We just keep moving on. Now, if we can swap, so this is smaller than this, right? Then we shall swap with this. Or we do not swap. If we do not swap, then this one move on, we do this, right? And this we don't swap, so we move on. But then this will be wrong, right? Then that's not DP. That's like 2 pointers, which I don't think is right. Yeah, what we're asking is to find the smallest number of operations to make this strictly increasing using this, right? That's the question. So how can we find this answer, let's say, by all the other combinations? Like I say, if I know the smallest of this and this, if I know that, okay, if I know that, then can I know this? Yeah, because you say if I don't swap, then it's this and this, right? If I do swap, then it's this and this. Interesting idea now. So we have ij, right? We want to find dpij. And we say if array I, right, is, because this one keep going larger. So if array I is smaller or equal to array 2j, then we just skip. Because if this is smaller or equal to this, right, they're corresponding, then there's no benefit of swapping. So in this case, we just keep going on. I plus 1, j plus 1. Right? Otherwise, if array y is smaller than this, okay, then we can say we can skip, right? So we can also skip. So we say skip, that's going to be dp I plus 1 j. It's this and this, okay? Or I don't skip, right? Or I swap. Then we do the swap. Then it's going to be dp I plus 1 j plus 1. Now, of course, this is the minimum, and I will also need to know the starting value. So we probably return two things, right? And we have to compare to see if it's possible. I want to give this a shot. Wait, how do I give this a shot then? I was thinking, what if we have lots of duplicates? I'm gonna try this, and if it doesn't work, I'm not trying anymore. I'm thinking about, what are you thinking about? I'm thinking about this. ij, and then I'm going to return a tuple of int and int. Right, and then from func_tools, I'm going to cache this thing for sure. Right, then what? If I is larger or equal to this, return, what do we return? Mean operations and first and array1I, right? Altered array1I after operation, after the function call. So if I is larger than n, so we're trying to find something here which does not exist. So minimum operation is going to be 0, which means we don't do any operation, right? And let's say we just return this. So if that's the case, now we're at ij. Then we say if array 1I is smaller or equal to array 2j, then we don't make any change. We just return helper I plus 1, j plus 1. We say in this situation, swapping will not make things any better. Okay, now array 1I is smaller, right? Then we can say skip, do not swap. Then that's option 1 is going to be op1 and next array 1 is going to be helper I plus 1j, right? And then we say if, because I do not swap, so if the next one is smaller or equal to array 1I, then op1 shall become math.inf. Means this is impossible. Or we can swap. Then op2 and next array 1 shall equal to helper I plus 1, j plus 1. Right? I plus 1, j plus 1, because I swap the current and then we just move on. Now it's op2. Again, I do think we have to do the same. No, I don't really think we need to do the same. But what if hold on, let me think. You say now you swap, right? In the next one, you can choose not swapping. And if not swapping is good, yeah, I don't think this one works. Because if the next one you don't swap, I give up. What did I do last time? Have any hints? What the heck is this thing? Initialize with value -1, which takes 0 steps into read. Okay. We go through every one in A, and for each A, I have a default dict, that's fine. For KV value step, what is this value step? Swap. What is K? What the hell is K? while the current value is larger or smaller than previous value. And I bisect on array 2. Huh? Okay, I see. Yeah, you don't need, you can remove duplicates because duplicate doesn't really matter. So you swap array 2, find k plus 1. That is value. It's value and step. So the value is going to be array 1, right? Okay, value is in array 1. So you're saying for this value to be good, for this value to be good, how many steps do we need to take? Is that what it is? For each, I think it's saying for each value that you make change or whatever in array 1, what is the minimum number of steps to reach there? Is that what it is? It doesn't seem, because I just return minimum on the value steps. But you can accumulate, right? You can accumulate. So for each thing, okay, what do I store? I store the minimum. I store the minimum number of steps needed to achieve a certain value. Huh. So given me, this is my current value, right? And I have everybody smaller than me. And I want to know what is this. If I smaller to reach this, say this number of steps to reach this, then what is the smallest to reach me? Hold on, let me think again. If I start and I swap, okay, I say I take 2 steps, 2 operations to reach this, whatever value. And now I come in and I need to find, I don't understand. Do it one more time. Swap index array 2 and a k plus 1. I mean, k plus 1, I think this probably is the current value, right? The current, not the current, it's all the values, because I go through the entire value step. I go through all the values that's in the value step, and I try to find what can we swap. If swapping gives fewer wait, this feels like Dijkstra. Right? This feels like Dijkstra. I'm updating the number of steps, right? If the new step give me better, and then I'm updating it. So I say in the previous, to reach these values, right? To reach these values, to reach this value, I take this number of steps. To reach this value, I take this number of steps. Okay. Then I say, I try to find k plus 1, the next value, right? Okay, I find the next value in there. We find it. Okay, we found the next value. And then we say, we try to see if the next value, if we have reached this next value already, that means, wait, hold on, what that mean? We have the next value, right? Whatever the value is, it plus 1, we find the next possible value if we want to swap to this value, because we take v number of steps to reach k, right? V number of steps to reach k. So if we swap, right, if we take the swap for the next one, then to reach the next one is going to be v plus 1 step. And if the v plus 1 step is smaller than whatever it is, then the next one shall be updated to v plus 1. And not swap, but still need to check whether value a has occurred before. Okay, then we say if a is larger than k, and v is smaller than temp a, a is larger than k, huh? If a is larger than k, what does that mean? A is larger than k. I mean, if a is smaller than k, if a is smaller than k, then no, we don't swap. If a is larger than k, and v is smaller than temp a, v is the number of steps, temp a is the number of steps to reach a, then we say the number to reach a is going to be v. This feels to me is swapping. It's not swap. I don't understand. What's inside the value step? I think inside the value step is all the values. Is the number of steps to reach whatever value, right? Whatever value. So number of steps to reach this value, number of steps to reach this value. It doesn't really matter. Number of steps to reach all these values. And then we will try array 2 to find the number of steps to reach this. Basically what we're saying is for each A, we want to find out the smallest number of ways to reach all possible values across the board. All right, all possible values across the board. And then we try to see if then what do we see? What are we seeing? Right, so we have KV, right? If A is smaller than K, then we definitely don't want to swap with K, right? We do not want to swap with K. That is reasonable, right? That is reasonable. We don't want to swap with K. Yeah, I think these K a value step, right? We only record value step. What is value step? I don't understand my solution. What are we looking for? We aim to make the prefix sorted in case array 1I requires replacement with a value from array 2. The smallest element in array 2 that will maintain the increasing order is always preferred. We can efficiently identify the smallest element that meets this criteria using binary search, which takes logarithm. Is not sorted. We will want to search the entire array to find it. Yes, that makes sense, right? So we want to have whatever the previous is always sorted, and then now we need to find the best to put in. Okay, we update from left to right. Each element array I can be subject to several potential operations. If array I is less than or equal to, we must replace with the smallest value in array 2 that is greater than, which we can binary such. Yes. If this is greater than, we have two options. Leave it unchanged. Yes. Replace it with the smallest value. That's exactly what I wrote here, right? And how does this one make it better? If the previous is larger than, it's like this situation. But it's a lot more complicated. we modify array 1i based on the value of this. Which represents the value of this. Yeah, so we just replace with 2. It's the same idea. It's exactly the same idea, but just better DP. Well, no, it's more than just better DP. Set array 2 and then sorted array 2. No, I and pre. Yeah, we need to do pre. Let's see. We can do it. You can say if array I is already, it's like greedy, right? If this is already like what I did here, if it's already larger than previous. No. If it's smaller or equal to previous, must swap, right? If the current is smaller than the previous value, then we must swap. And which one do we swap? We swap by, you can say j equal to bisect right, array 2, and the pre has to be larger than that, okay? Then we say if j is smaller than m, if j is smaller than m, then we do the swap. We shall return 1 plus helper I plus 1 array 2j, right? Else, then we should return math.inf. Either swap or not swap. So now we say array I is larger than pre. We can swap, and we can skip swapping. Skip swap. So what do you mean by skip swap? Yeah, we just ignore it. We go for the next one, which is just helper I plus 1. Same? No. Should be array 1I. That's the previous value, right? So option 1 is equal to this. or we can swap, and it'll be the same, right? J equal to bisect right, 2 pre, and if j is smaller than m, OP2 is 1 plus helper I plus 1 array 2j, else OP2 math.inf. And now we return the minimum of OP1 and OP2. Now we return helper 0 and -1. Option 1, always swap. Option 2, do not swap, but this only applies when array 1I is larger than pre. Right, if array 1 is larger than pre, then we do not swap. Then option 2 equal to this, right? Do not swap. Else using this, what was I trying to do? Well, this is a number of operations. That's different. This is, yeah, this is timeout. Man, this is, how should I put it? I don't even need this. I never used M. Oh, I did use M. Nah, I'll just line array 2 then. This is the same, line array 1. Yeah, I think this is much better than than the other attempt. Let's see if this is right. So 1187. I mean, the general idea in solution 1 is correct, but we used the wrong state for DP. I mean, technically speaking, I was not doing DP in solution 1, but backtracking. The correct state is the current index of array 1 and the previous value in array 1, right? Then at each index of array 1, we have two choices. Either swap with the smallest value in array 2 that still satisfies array 1 being increasing, or do not swap, which can only happen if the current array 1 index value is larger than the previous one. Yep. What's the runtime on this then? Actually, I have no idea what the runtime is. I mean, we don't get all pre, right? Because this depends on how many values in total do we have, right? We have n number of this. We have at most n plus m number of this. And then we need to do log this. So m times n log m plus n. Is that what this one says? At most n plus 1 pre. Yeah, it's n plus 1 pre. This is all log n. What is m? M indices at most n plus 1 possible. I think this... I don't think this is right. I don't think this is right. I do not think this is right. We have, if we say the length of this is n, the length of this is m. Worst case scenario, we go through all combinations, right? And all combinations, we shall have n number on this, and this we have n plus m different combinations, because we pick something from array 2 and then we pick something from array 1, right? So that shall be n. So here's what I think. I think this is n times m plus n log m plus n log m. That's what I think. If this is log m. Yeah, this is what I think. Well, does this pass? It does, right? It does. Back to the square one about DP, right? What is the most important part of DP? Figure out the state. I mean, you have the right idea, but the state was wrong. The state is the previous value. Because when you do the DP, what matters is the previous value. I mean, you're almost there, right? You're almost there. The previous value is the most important. The current value and the previous value, and depending on the previous value. And that's actually how you avoid backtracking. And the reason you need to do the backtracking because you're changing the value. And as you change the value, the reason you change the value is because you want to compare it again, right? You do this comparison. You are comparing with the previous value. Like here, you are comparing with the previous value. And when you do that, you have to backtrack. And it's not the best way because you can just put the previous value as part of the state. Then you don't have to make any changes to the original array. You can compare directly to the only value that matters. Pretty cool, huh? All right, that will be it for today. Took a long